Attosecond physics. File HighharmonicGeneration.jpg %7c 328x328x High-harmonics generation and krypton. This technology is one of the most used techniques to generate attosecond bursts of light. Attosecond physics, also known as attophysics, or more generally attosecond science, is a branch of physics that deals with light-matter interaction phenomena wherein attosecond 10-18s photon pulses are used to unravel dynamical processes in matter with unprecedented time resolution. Attosecond science mainly employs pump-probe spectroscopic methods to investigate the physical process of interest. Due to the complexity of this field of study, it generally requires a synergistic interplay between state-of-the-art experimental setup and advanced theoretical tools to interpret the data collected from attosecond experiments. The main interests of attosecond physics are 1. Atomic physics, investigation of electron correlation effects, photo-emission delay and ionization tunneling. 2. Molecular physics and molecular chemistry, role of electronic motion in molecular excited states e.g., charge transfer processes, light-induced photofragmentation and light-induced electron transfer processes. 3. Solid-state physics, investigation of exciton dynamics in advanced 2D materials, petahertz charge carrier motion in solids, spin dynamics in ferromagnetic materials. One of the primary goals of attosecond science is to provide advanced insights into the quantum dynamics of electrons in atoms, molecules and solids with the long-term challenge of achieving real-time control of the electron motion in matter. The current world record for the shortest light pulse generated by human technology is 43 years. In 2022, Anel Hewlett, Paul Corkum, Ferenc Cross are awarded with the Wolf Prize in Physics for their pioneering contributions to ultra-fast laser science and attosecond physics. Introduction. The advent of broadband solid-state titanium-doped sapphire-based high-SAW lasers 1986, chip pulse amplification CPA 1988, spectral broadening of high-energy pulses e.g., gas-filled hollow core fiber via self-phase modulation 1996, mirror dispersion control technology chart mirrors 1994 and carrier envelope offset stabilization 2003 had enabled the creation of isolated attosecond light pulses generated by the nonlinear process of high harmonics generation in a noble gas 20,040 2006, which have given birth to the field of attosecond science. File breath weapon %7c 7c 324x electron motion in a hydrogen atom. The period of the state superposition once swap is around 400 s. Motivation to attosecond physics. The natural time scale of electron motion in atoms, molecules, and solids is the attosecond one as equals 10-18s. This fact is a direct consequence of quantum mechanics laws. Indeed, for simplicity, consider quantum particle in superposition between ground level at energy letter 3f5 and the first excited level of energy letter 3f5. Psi equals Cg psi g plus Ce psi e, with Ce and Cg chosen as the square roots of the quantum probability of observing the particle in a corresponding state. $psi gt. Angle equals 0. Angle E \frac I epsilon 0 h bar t q chord psi et. Angle equals 1. Angle E \frac I epsilon 1 h bar t dollar are the time-dependent ground 0 and excited state 1 respectively, with ladder 210 f the reduced Planck constant. The expectation value of a generic emission and symmetric operator can be written as pt equals psi. As a consequence, the time evolution of this observable is $pt equals Cg2 angle 0 hat p0 angle plus Ce2 Langliern hat p1 angle plus torque g angle 0 hat p1 angle gauss frac epsilon 1 epsilon 0 h bar t dollar. While the first two terms do not depend on time, the third instead does. This creates a dynamic for the observable pt with a characteristic time tc given by $tc equals frac 2 pi h bar epsilon 1 epsilon $0. As a consequence, for energy levels in the range of Letta 3F5 1 minus Letta 3F5 approximately 10 eV, which is the typical electronic energy range in matter, the characteristic time of the dynamics of any associated physical observable is approximately 400 s. To measure the time evolution of PT, one needs to use a control tool or a process with an even shorter time duration that can interact with the dynamic. This is the reason why Attosecond light pulses are used to disclose the physics of ultrafast phenomena in the few femtosecond and attosecond time domain. Generation of Attosecond pulses. To generate a traveling pulse with an ultrashort time duration, two key elements are needed: bandwidth and central wavelength of the electromagnetic wave. From Fourier analysis, the more the available spectral bandwidth of a light pulse, the shorter, potentially, is its time duration. There is, however, a lower limit in the minimum duration exploitable for a given pulse central wavelength. This limit is the optical cycle. Indeed, for a pulse centered in a low frequency region, e.g., infrared IR lambda equals 800 nm, its minimum time duration is around $d pulse equals \frac lambda c equals $2.67 fs, where c is the speed of light, whereas, for a light field with central wavelength in the extreme ultraviolet XUV at lambda equals 30 nm, the minimum duration is around t pulse equals 100 s. Thus, a smaller time duration requires the use of shorter and more energetic wavelength, even down to the soft X-ray SXR region. For this reason, standard techniques to create Attosecond light pulses are based on radiation sources with broad spectral bandwidths and central wavelength located in XUV SXR range. The most common sources that fit these requirements are free electron lasers FEL and high-harmonics generation HHG setups. Physical observables and Attosecond experiments. Once an Attosecond light source is available, one has to drive the pulse towards the sample of interest and then measure its dynamics. The most suitable experimental observables to analyze the electron dynamics in matter are angular asymmetry in the velocity distribution of molecular photofragment, quantum yield of molecular photofragments, XUV SXR spectrum transient absorption, XUV SXR spectrum transient reflectivity, photoelectron kinetic energy distribution. The general strategy is to use a pump probe scheme to image through one of the aforementioned observables the ultrafast dynamics occurring in the material under investigation. View femtosecond IR XUV/SXR Attosecond pulse pump probe experiments. As an example, in a typical pump probe experimental apparatus, an Attosecond XUV SXR pulse and an intense 10-10 W/cm2 low frequency infrared pulse with a time duration of few to tens femtoseconds are collinearly focused on the studied sample. At this point, by varying the delay of the Attosecond pulse, which could be pump/probe depending on the experiment, with respect to the IR pulse probe/pump, the desired physical observable is recorded. The subsequent challenge is to interpret the collected data and retrieve fundamental information on the hidden dynamics and quantum processes occurring in the sample. This can be achieved with advanced theoretical tools and numerical calculations. By exploiting this experimental scheme, several kinds of dynamics can be explored in atoms, molecules, then solids, typically light-induced dynamics and out-of-equilibrium excited states within Attosecond time resolution. Quantum mechanics foundations. Attosecond physics typically deals with non-relativistic bounded particles and employs electromagnetic fields with a moderately high intensity 10-10 W/cm2. This fact allows to set up a discussion in a non-relativistic and semi-classical quantum mechanics environment for light-matter interaction. Resolution of time-dependent Schrödinger equation in an electromagnetic field. The time evolution of a single electronic wave function in an atom site is described by the Schrödinger equation in atomic units. $h/sit. Angle equals I/d frac /partial t/sit. Angle /quad $1.0. With a light-matter interaction, Hamiltonian can be expressed in the length gauge within the dipole approximation as $h equals \frac 1 2 text p2 plus vc plus \text far \c dot text et $. where Vc is the Coulomb potential of the atomic species considered $hat\text p\hat\text $var are the momentum and position operator, respectively, and ed is the total electric field evaluated in the neighbor of the atom. The formal solution of the Schrödinger equation is given by the propagative formalism. Psi equals E minus I integral T psi 1.1, where psi is the electron wave function at time t equals t. This exact solution cannot be used for almost any practical purpose. However, it can be proved, using Dyson's equations, that the previous solution can also be written as psi equals minus I integral t dt plus E minus I integral t0 t dt psi 1.2, where $HDO equals \frac 1 2 \text p2 plus vc is the bounded Hamiltonian, and $H equals \text var c text vt is the interaction Hamiltonian. The formal solution of EC 1.0, which previously was simply written as EC 1.1, can now be regarded in EC 1.2 as a superposition of different quantum paths or quantum trajectory, each one of them with a peculiar interaction time t with the electric field. In other words, each quantum path is characterized by 3 steps. 1. An initial evolution without the electromagnetic field. This is described by the left-hand side H0 term in the integral. 2. Then a kick from the electromagnetic field that excites the electron. This event occurs at an arbitrary time that univocally characterizes the quantum path t. 3. Final evolution driven by both the field and the Coulomb potential given by. In parallel, you also have a quantum path that do not perceive the field at all. This trajectory is indicated by the right-hand side term in EC 1.2. This process is entirely time reversible, that is, can also occur in the opposite order. Equation 1.2 is not straightforward to handle. However, physicists use it as the starting point for numerical calculation, more advanced discussion, or several approximations. For strong field interaction problems, where ionization may occur, one can imagine to project EC 1.2 in a certain continuum state, unbounded state, or free state p of momentum p, so that CPT equals p psi equals minus I integral t dt p minus I integral t dt it minus I integral t to 0 t dt psi plus p minus I integral t 0 t dt psi 1.3. CPT2 is the probability amplitude defined at a certain time t, the electron in a continuum states p. If this probability amplitude is greater than 0, then the electron is photoionized. For the majority of application, the second term in 1.3 is not considered, and only the first one is used in discussions. Hence, pt equals minus I integral t dt p minus I integral t dt hit minus I integral t to 0 t dt psi 1.4. Equation 1.4 is also known as time-reversed S-matrix amplitude, and it gives the probability of photoionization by a generic time-varying electric field. Strong field approximation SFA. Strong field approximation SFA. Strong field approximation SFA, or Kuldish-Feisel-Rias theory, is a physical model started in 1964 by the Russian physicist Kuldish, is currently used to describe the behavior of atoms and molecules in intense laser fields. SFA is a starting theory for discussing both high harmonic generation and Attosecond pump probe interaction with atoms. The main assumption made in SFA is that the free electron dynamics is dominated by the laser field, while the Coulomb potential is regarded as a negligible perturbation. This fact reshapes equation 1.4 into PSFET equals minus I integral t dt p minus I integral t vt dt hit minus I integral t to 0 t dt psi 1.4, where $HV equals \frac 1 2 \text p plus \text for t2 is the Volkov Hamiltonian, here expressed for simplicity in the velocity gauge, with that $text vt equals \frac partial \text for t partial t the electromagnetic vector potential. At this point, to keep the discussion at its basic level, let's consider an atom with a single energy level 0, ionization energy IP, and populated by a single electron, single active electron approximation. We can consider the initial time of the wave function dynamics as t0 equals minus infinity, and we can assume that initially the electron is in the atomic ground state 0, so that 0 equals minus I p0 and psi equals e minus I integral minus infinity to 0 dt0 equals e I pt0. Moreover, we can regard the continuum states as plane wave function state $\lango\text file \text p angle equals 2 /pi /frac re 2 e \text p /c dot \text var $. This is a rather simplified assumption. A more reasonable choice would have been to use as continuum state the exact atom scattering states. The time evolution of simple plane wave states with the Volkoff-Hamiltonian is given by p minus I integral t t v t dt equals b plus a d minus I integral t t b plus a t dt. Here, for consistency with AC 1.4, the evolution has already been properly converted into the length gauge. As a consequence, the final momentum distribution of a single electron in a single level atom with ionization potential IP is expressed as a pt SFA equals minus I integral minus infinity t at plus I pt minus int t 1.5, where $text d equals \lango \text p plus \text for t hat \text for 0 angle $. Is the dipole expectation value or transition dipole moment, and $cent t equals int tt frac 12 \text b plus \text for t $, is a semi-classical action. The result of EC 1.5 is the basic tool to understand phenomena like the high harmonics generation process, which is typically the result of strong field interaction of noble gases with an intense low frequency pulse, Attosecond pump probe experiments with simple atoms. The debate on tunneling time. Weak Attosecond pulse, strong IR fields, atoms interactions. Attosecond pump probe experiments with simple atoms is a fundamental tool to measure the time duration of an Attosecond pulse and to explore several quantum properties of matter. 5 Quantum Interaction 3 JPG % 7C thumb % 7C 312x 7C scheme of a strong IR field and a delayed Attosecond XUV pulse interacting with a single electron in a single level atom. The XUV can ionize the electron, which jumps in the continuum bidirect ionization blue path in the figure. The IR pulse, later, streaks up and down in energy the photoelectron. After the interaction, the electron has final energy, which can be subsequently detected and measured e.g. time of flight apparatus. The multi-photon ionization process red path in the figure is also possible, but since it is relevant in different energetic region, it can be disregarded. This kind of experiments can be easily described within strong field approximation by exploiting the results of EC 1.5 as discussed below. As a simple model, consider the interaction between a single active electron in a single level atom and two fields, an intense femtosecond infrared IR pulse ERT, and a weak Attosecond pulse centered in the extreme ultraviolet XUV region EZUVT. Then, by substituting these fields to 1.5, it results a pt equals minus I integral minus infinity t EZUVT plus ERT de plus II pt minus int t 1.6. With $cent t equals int tt frac 12 text p plus text var t plus text for xuvt $. At this point, we can divide EC 1.6 in two contributions, direct ionization and strong field ionization multiphoton regime, respectively. Typically, these two terms are relevant in different energetic regions of the continuum. Consequently, for typical experimental condition, the latter process is disregarded, and only direct ionization from the Attosecond pulse is considered. Then, since the Attosecond pulse is weaker than the infrared one, it holds EZUVT. Thus, EZUVT is typically neglected in EC 1.6. In addition to that, we can rewrite the Attosecond pulse as a delayed function with respect to the IR field. Therefore, the probability distribution β2 of finding an electron ionized in a continuum with momentum p after the interaction has occurred at t equals infinity in a pump probe experiments with an intense IR pulse and a delayed Attosecond XUV pulse is given by p2 equals minus I integral minus infinity EZUVT minus t to plus II pt minus st dt 1.7, with $cent equals \frac 12 text p twat plus int t inf t text p c text for t plus frac 12 text for t twat. Equation 1.7 describes the photoionization phenomenon of two-color interaction XUVIO with a single-level atom and single active electron. This peculiar result can be regarded as a quantum interference process between all the possible ionization paths, started by a delayed XUV Attosecond pulse, with the following motion in the continuum states driven by a strong IR field. The resulting 2D photoelectron momentum, or equivalently energy vs delayed distribution, is called streaking trace. Attosecond techniques. Here are listed and discussed some of the most common techniques and approaches pursued in Attosecond research centers. Attosecond metrology with photoelectron spectroscopy frog crab. Attosecond metrology with photoelectron spectroscopy frog crab. A daily challenge in Attosecond science is to characterize the temporal properties of the Attosecond pulses used in any pump probe experiments with atoms, molecules, or solids. The most used technique is based on the frequency-resolved optical gating for a complete reconstruction of Attosecond bursts frog crab. The main advantage of this technique is that it allows to exploit the corroborated frog technique developed in 1991 for picosecond femtosecond pulse characterization to the Attosecond field. Crab is an extension of frog and it is based on the same idea for the field reconstruction. In other words, frog crab is based on the conversion of an Attosecond pulse into an electron wave packet that is freed in the continuum by atomic photoionization, as already described with EC. 1.7. The role of the low-frequency driving laser pulse, e.g. infrared pulse, is to behave as gate for the temporal measurement. Then, by exploring different delays between the low frequency and the Attosecond pulse, a streaking trace or streaking spectrogram can be obtained. This 2D spectrogram is later analyzed by a reconstruction algorithm with the goal of retrieving both the Attosecond pulse and the IR pulse, with no need of a prior knowledge on any of them. However, as EC. 1.7 pinpoints, the intrinsic limits of this technique is the knowledge on atomic dipole properties, in particular on the atomic dipole quantum phase. The reconstruction of both the low-frequency field and the Attosecond pulse from a streaking trace is typically achieved through iterative algorithms such as Principal Component Generalized Projections Algorithm PCGPA, Volkov Transform Generalized Projection Algorithm BTGPA, Extended Tetrographic Iterative Engine EPAE. Attosecond groups in the world. University of Nebraska-Lincoln Max Planck Institute of Quantum Optics, Munich Lund University ELI Leipzig Stanford University Politecnico Milano CE Paris Max Bonn Institute, Berlin University of Freiburg GES Laborator Imperial College London Seefeld Hamburg IQUA Barcelona OSU Columbus ETH 4th Heraclean Griffith University, Queensland Weizmann Institute of Science, Tel Aviv Reich and Tokyo Heidelberg University of China Riyadh ETH Zurich. Category Quantum Mechanics. Category Atomic, Molecular, and Optical Physics. Category Articles containing video clips. Category Time-resolved spectroscopy.